Hey guys, welcome back to another episode on complex numbers, and today we are going to be looking at some ARGAND diagrams, and perhaps maybe if we don't go over too much in time, we'll do the locus of a complex number, also diagrams. So we're trying to get in one video all of those diagrams. So let's begin. What do we know about diagrams in math? Well, you all know what the Cartesian plane looks like, right? Remember that? We have our x and our y axis. So sometimes you may have a point P, and that point has an x and y coordinate. And we also name our axes accordingly. The x-axis is horizontal and the y-axis is vertical. And this here is called our origin. Now, this is for the Cartesian plane that everybody becomes familiar with once you start plotting points to draw straight line graphs or quadratics, etc. But you see, now you guys have been just introduced to something called the complex number system. Okay? And when it comes to the complex number system, if you would like to represent complex numbers on a plane, it's going to have to be a different plane because we have some kind of imaginary part attached to it. So complex numbers are generally plotted on something called a complex plane instead of the Cartesian plane. And it's no rocket science. The only thing that actually makes a Cartesian plane different from a complex plane are how we rename the axes. So let's switch it up right now. Okay, so going from the Cartesian plane into the complex plane, let's recall what the general form of a complex number looks like. It's usually in the form x plus iy or yi. And yes, you're seeing components of x and y present, but that doesn't mean that it's plottable on the Cartesian plane, okay? What we do need to understand is that one part of a complex number is real, and the other part is imaginary. And those are what we're going to use to represent the renaming of our axes. So the horizontal axis for a complex plane is actually renamed as, it's a shorthand version, the real part. I usually like to write my z with a cross in the middle. You guys do not have to, but it's just, you know, what I do. And the vertical axis is the imaginary part, and it's represented by the denotation Im of z. So this is how you would rename your axes when you're moving from the Cartesian plane to the complex plane and you want to plot complex numbers on there. Okay? Now, essentially, when you're using the Cartesian plane, and you're drawing like graphs, you have special names for it. You call it a straight line graph, or you call it a quadratic, etc. You know, you have special names for it. Now, when you're plotting complex numbers on the complex plane, these diagrams have a special name, and they are called dun, 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 ARGAND diagrams. I don't know, I feel like that's a thing they would say in Sesame Street. But yeah, that's what they call it. So anytime you have to plot a complex number on a complex plane, it has a name. It's called an ARGAND diagram. And it's actually very straightforward. Complex numbers are just like vectors. They're like straight lines. For example, you know, when you have a position vector, like for example, OB, it has a specific format, and you write it like that, and this simply means that you have a vector starting from the origin, ending somewhere here, and in order to plot it, this would be the x value, and this would be the y value, right? Well, similarly, when you have a complex number, okay, you're gonna treat it just like you would vectors. And let me give you an example so you can see how we actually plot it. Let's just consider we have a complex number z being equal to 3 plus I. Okay, and first of all, we got to identify our real parts and our imaginary parts to plot. That's why we have the axes named real and imaginary. Those are actually the values you plot. So this is the real part, and this is the imaginary part. Remember, just the coefficient. So the real value is 3, and the imaginary value is 1, positive 1. And the first value, if we consider this in the form x plus iy or yi, then that means our first value here is also like the x value, and the second one is the y value, if you want to think of it like that for future purposes. There's formulas you're going to see where you're going to have to be able to relate the real part to the value x and the imaginary part to the value y. Okay, but for now, we want to plot this complex number 3 plus I onto our complex plane. And here's how easy it goes. The real part is 3. So we're going to, just like you would, set up your scale and whatnot on your x and your y axis. You would do it for your real and imaginary axes as well. And the first value, the real value, goes over here. And you go up till you see the corresponding imaginary value of 1 that you're looking for. Okay, and that's around here. And that means that we could connect just like you would a position vector. You would simply connect from your origin, you would connect to that point there. And that is how you would represent your complex number on an ARGAND diagram. That's the final answer. And some people, they like to write in the coordinate that they plotted onto the graph page, and also generally because it's considered to be a vector in essence, what usually happens is that we have an arrow included showing the direction of that complex number. Okay, and sometimes you may see that the complex number can also be represented as a vector. So this complex number could be represented as 3, 1 as well. Okay, so that's as easy as it goes. I can give you guys a second example. So we call this Z1. Okay, so this line in red here is the complex number Z1. Let's do Z2. Let's see if we had something like, let's keep it to the positive quadrant there, the first quadrant, because I only, I should have extended it, but that's fine. How about we have something like 4 plus 2i. Okay, so this part here is the real part. This is the imaginary part. So we're looking at plotting 4 with 2. So we just go ahead, 4 with 2, that's around here, connect from the origin, okay, and you draw your little arrow. You can call it Z2 if you like. You can include the coordinate 4, 2 at the end, but that's pretty much how you would represent a complex number on an ARGAND diagram. Now, we're also going to learn 2 very important formulas coming up next. So because of that, I would also like to show you guys, before we even get there, what a complete ARGAND diagram should really look like. Now, because essentially a complex number looks like a vector or a straight line on a complex plane, that straight line is always going to form some sort of angle with the horizontal real axis there, right? It's going to form an angle called theta. Now, when you're doing a complete ARGAND diagram, you would have to also include that value of theta on your diagram for it to be considered fully labeled, okay? So for example, the first one in red, I would probably put theta 1, and for the one in purple, I would, if I can fit it on here, I'll put theta 2, just so you guys can be able to differentiate that it's two separate complex numbers there. Okay, and for now, for this moment, because you're being introduced to it, I'll allow you guys to call it theta for the moment, but it actually has another name. Okay, so that's actually coming up next. So main part, get some practice drawing some straight lines. It'll beef up your memory skills on plotting straight lines and points and such. The only thing that you really need to change is your interpretation of the horizontal and that vertical axis becoming the real and imaginary axes instead. Right? Very easy transition. I don't think it should give you too many issues. And yeah, I think you guys are going to enjoy this topic also. Like I said, complex numbers is such a beautiful, beautiful topic. You're going to love it. So stay tuned. Coming up next, those formulas I was telling you guys about. So hold on. Okay, so we are back, and on screen I have just a little setup of the complex plane again, denoted by the change in the renaming of the axes, right? Now, like I was saying, a complex number looks like a vector, a straight line, right? And as with all straight lines, we can actually find the length of the line. Okay, so this line here in purple, I'm going to put in arrows to denote like a direction. And you can find the length of that line. Let's just say this point was called P. Okay, then we can find the length of OP. All right, now when it comes to finding the length, you guys who are doing physics would also be very familiar with the word modulus. And you should be familiar with it from Form 5 as well. Modulus means length. Okay, so when you hear the term modulus of something, they want you to find the length, and usually it's the length of a straight line. Now, there's a denotation, and there's also a formula I'm going to put on screen for finding the length of any complex, well, any length of the straight line that you have plotted to represent a complex number, and it goes like this. It's R for any given complex number z equals x plus iy. Let me write that in. For any complex number z in the form x plus iy or yi, however you want to represent it, the modulus, denoted by the modulus of z, okay, is also denoted by the letter r, and you can think of it as a radius if you want to, because if you were to spin, if you were to hold your finger at the origin and let the point P spin all the way around the 4 quadrants, it would form a circle such that R is a radius, okay? So the modulus of C, denoted by those parallel bars, okay, takes the formula, the square root of x squared plus y squared. So very, very nice and simple. Let me give you guys an example on screen how we would apply the formula. Let's consider we had a complex number such that z is equal to 2 plus I. Then, using the formula, in a nutshell, the length of that is simply equal to the square root of x squared plus y squared. Remember that x comes from the first part and y comes from the second part. So actually, if it were rearranged as I plus 2, then you would have to remember that x is the real part, okay? But because you're adding and squaring, I don't think it's really going to matter because addition is commutative. So 2 squared plus 1 squared is the same as 1 squared plus 2 squared, just in case you mix up the formula. It's going to be fine. And that's just simply going to give you the square root of 5, okay? And I would also probably throw it in there that you can add the words units, because it is a length after all, okay? So if our complex number were z equal 2 plus I, first of all, if you were wondering what to plot, to represent this, you would plot positive 2 with 1, and that would be say this was 1, this was 2, that would be 2. And let's put our 1 up here, okay? So that this would represent our z. Okay, and if you wanted to find out the length or radius of that complex number up there, it's just going to be equal to the square root of its real part squared plus the imaginary part squared. And the answer is simply square root of 5. I'm not going to do too many examples with this because I think it's pretty much straightforward. So let's just go ahead and get into the second part where we need to find the value for the angle that a complex number makes with the horizontal axis or that real axis there. So up next, hold on. All right, so let's draw our complex plane again. I decided to draw it with you so that you can see the process and it can sink into your memory. That's how we name the horizontal axis for a complex plane, imaginary part of z. And let's just say we had a complex number that looks somewhat like that. We're going to put an arrow on, okay? Now, I was saying that there's formulas for not only the length of that complex number, if you can remember from just 2 seconds ago, okay? You also have an angle that is formed to the horizontal axis with complex numbers, and there's also a formula and a new name to call that angle. Now, typically when you're dealing with a Cartesian coordinate, you know that this is called theta, okay? But when we're dealing with a complex plane, we actually have a different denotation and name for it. The angle is called the argument, denoted by ARG of z. So not so much theta, it's called the argument of z, okay? And that theta, if you want to call it that theta, which is the argument of z, has a formula. And the formula is as follows, okay? Now, I'm choosing to show you the formula first because I actually want to show you guys how they derived it, okay? Now, let's just consider that for this complex number, there were arbitrary values that had to be plotted, general values, okay? Now, this vertical line obviously is going to represent the y value. So if this was 5, from here to here would be the y value. And from here to here would be the x value, okay? So therefore, here is your x. And let me take off that 5. Now, with angles, if you think in terms of so, ka, to, wa, right? Shaking up your memory skills here. Trigonometry, basic trigonometry. If you have the opposite and you have a value for the adjacent, then that means you have O and you have A. So it means that we're talking about tan of an angle. So for this little triangle that you can see here, if I were to outline it, okay, that's a right angle triangle. And for that right angle triangle, you can see that we have tan theta. Okay, if you remember your formulas, tan theta is simply going to be equal to the opposite, right? This is opposite, which is y, over the adjacent, which is x. All right, and if you wanted to make theta the subject of the formula, that would simply be tan inverse of y on x. And ta-da! That is how they ended up getting this formula here in red for the angle, okay, for the angle theta, preferably called the argument of c. All right, guys, so this is not a proof that's ever asked for, but at least in exams, if you you know, you blank out and you're wondering, is it X on Y? Is it Y on X? You can actually draw up your little diagram as follows, and you can deduce the formula yourself. Okay, so it always pays to really understand what you're doing, not so much cram or formulas straight off the bat. Okay, guys? So, in a nutshell, let me just recap what we learned so far. So you learned that you can plot complex numbers on something called a complex plane. All right. And on a complex plane, if you plot a complex number, it's called an ARGAND diagram. All right, an ARGAND diagram. And an ARGAND diagram looks kind of like if you just plotted a vector, which is a straight line. And with all vectors, all straight lines, you can do two things. You can find the length or the modulus of the line, and you can also find the angle. But for complex numbers, it's called the argument. And for both, you have formulas, okay? So for the length, this is the formula. For the argument, this is the formula. So let me just give you guys an example of how you would actually find both the length and angle for a diagram. So let's just clean this section up here. Okay. All right, let's go. I think I'll choose black. Yeah. Okay, let's go ahead here in this nice little space. Okay. And let's just say they asked us to find, so we didn't have to represent anything on a diagram. They just said, hey, we have a complex number, z is equal to -1 plus I. Can you find part A? Can you find the modulus or the length of that, or R? And part B, can you help us find the argument of that complex number? If the name of it is -1 plus I, then you are finding the argument of -1 plus I. If you wanted to write it as follows, if you didn't want to have to write all of that full complex number, you could also just write the argument of C. Now using the formula straight off the bat, you're going to get the square root of x squared plus y squared. And in this case, let me just denote, we have x here and we have y here. So x squared is -1 squared, which is just 1. And y squared is +1 squared, which is just 1. So we're going to get square root of 2 units. Okay. And the argument is given by the formula tan inverse of y on x. All right. And this is going to be, let's see, tan inverse of y has a value of 1 and x has a value of -1. Now, the thing is, when you're dealing with arguments, there's 3 special cases that I need to show you guys, right? So for this example over here, you're going to get tan inverse of, I think it is, well, tan inverse of -1, obviously. And if you go to your calculadora, I believe that's -1/4. So let me just minimize this for a second here. Okay, and let's just shift this up. And if you go to your calculator, tan inverse of -1 should produce a value of -pi/4 for those of you guys who know it off by heart, right? But unfortunately, this is not the final answer for a question like this. And that takes us into what we're going to learn up next. Okay, so let's get into it. Okay, so you see, as with the Cartesian plane, you also have 4 quadrants on your complex plane. Okay, and they're pretty much named the same. This is your first, this is your second, this is your third quadrant, and this is your fourth. And this is usually considered like your positive quadrant over here, okay? So when it comes to angles in math, you know, sometimes you have to add pi, sometimes you have to subtract pi based on how many revolutions you're making and stuff like that. Well, finding the argument of a complex number has a little bit of that involved. Okay, so here's where it would be easy. If you ever have to find the argument of a complex number that happens to lie in the first or the fourth quadrant, all right, you can use your formula tan inverse of y on x like nobody's business, and you can move on with your life, and your answers are not going to be affected. You don't have to do anything extra. But unfortunately, when you're finding the argument, and just say your complex number is going to lie in the second quadrant, then the formula remains the same, except there's just a little bit of an extra. You have to add pi to your final answer. Okay, and I'll explain why in just a second. If you're finding it in the third quadrant, you're gonna have to subtract pi from your final answer. Okay, and let me show you guys why. So a complex number that lies in the first quadrant looks like this. It'll be positive, positive, right? It'll be like 1 plus like 2i or something like that. So like this will be 1, and this will be like 1, 2. All right, and your value will be up here, and then you connect. And that's how you know that your complex number is lying in the first quadrant. And if you had to find the argument, you just use this formula and that's it. But what if you had, let me just erase this here. What if you had a complex number that looks like z is equal to -1 plus 2i? Then that would mean you would have your value lying here. That's -1 plotted with that 2 there. So over here is where your complex number is going to lie. Okay, so essentially, because the argument is measured from that real axis there, then theta is going to be this value all the way in blue. All of this is going to be theta, right? Now, that's fine. But the thing is, you see, when it comes to complex numbers, the value of theta is supposed to lie between -pi and pi. So when you have complex numbers that fall like in the third and the fourth quadrant, the value sometimes can be not within this range here. So to account for that, what we do is we simply have to like add pi. Okay, we add pi to make sure that our argument, our principal argument of z lies in the given range it's supposed to lie in. Okay, and similarly for the third quadrant, the same thing happens. If you have a complex number, and let's just say it lies somewhere around here, okay, then that would mean that the angle is actually from that horizontal axis all the way over here, which is this value here. So we would have to subtract pi, because you know, below, when you're going below that horizontal axis, you would have negative values and stuff like that. So subtracting pi helps us keep our answers within that range of -pi and pi. Okay, guys? And one final point about the angles, just take note that the argument is always measured in radians. Okay, it's radians. So when you're getting values of you know, like for example in this one here, if z were indeed 1 plus 2i, and we had to work out the value of the argument, that would be y is 2 over 1, and tan inverse of that is 2 over 1. Oh, I think I made up an example which is probably gonna give us a little bit of an error. Let me just change this example so it fits. Well, not so it fits. I mean, you're gonna get a decimal, and I kind of want to show you guys like a perfect radian value. You know, make sure to put your calculators on radian mode, by the way. because you'll end up getting the wrong answer, right? So in radian mode, this value would be like 1.11 radians. Remember, the symbol to represent radians is a little c. But what I really wanted to show you guys is an example where it's perfectly like with that pi value. So let's just say z was indeed just 1 plus pi. 1 plus I, sorry. Then tan inverse would be 1 over 1. And that gives us a perfect value of tan inverse of 1. And you all know that tan inverse of 1 is just pi on 4. So at this point, if you guys do not know those exact values, now would be a good time to go back and recap on your cos, well, mostly your tan, finding the exact and perfect values of tan inverse of numbers like 1, root 3 on 2, tan inverse of like, you know, the 60 degrees, 90 degrees, 30 degrees, all of that good stuff. Okay, guys, so yeah, when you're giving your argument, try to make sure you give it, not try, you have to give it in radians. Okay, so it's not that difficult. The two formulas, the length of the line and the angle, it's just that you have to remember whenever that your complex numbers happen to lie in the third and the fourth quadrant, to make sure you add pi or you subtract pi respectively. Okay, stay tuned. We're going to be looking at some more diagrams coming up next. Okay, and we're back. So on screen, you're seeing a topic called locus of a complex number. And the first thing that comes to mind when you hear the word locus is like location, you know, where something is at, and kind of like where the party is at, you know. Like, for example, where it's happening, you know. So we just did diagrams, ARGAND diagrams, to be precise, and you guys would have learned that, you know, an ARGAND diagram is just similar to a Cartesian plane, sorry. It's called a complex plane. And the axes are real and imaginary. And you learn how, if you were given a standard complex number such as x plus iy, that you would use those values x and y, and you would just represent them like a vector onto your complex plane. And that's what that complex number is going to look like. But sometimes there's like not just a situation where they want to know the location of just that complex number. They kind of want to know something called a locus, which is kind of like the area around it, more appropriately like a circular area. Sometimes it could be like an area parallel to it, it could be an area perpendicular to it, just different stuff, right? They want to know regions around it, and those regions have something called conditions. Okay, so it's pretty much like, let me explain using an example. Let's just say we have a complex number z, and it's 1 plus I. Okay, if you had to plot that, here's 1, here's 1, this would be 1 plus I here. Okay, this is the point 1, 1. That's a complex number if we were to connect here to here. That's your complex number there. You could put in your theta if you wanted to. But that's if the question asks you to draw this. This is just an ARGAND diagram. Now, sometimes you will see special conditions and you will recognize it by the format it is given in. So one of the first formats that shows you need to draw a circle. Okay, so let me highlight that. One of the first things you're gonna have to do is draw a circle, and the condition of the format that helps you to recognize you have to draw a circle is that you will be given a complex number within a system that looks something like this. I know it looks scary, but here is an example. Okay, so for example, C is actually the complex number that you're plotting. Z is just a system. Okay, so let's just say you had something like this, C minus, and the complex number you're given is 1 plus I. All right, and that is equal to, let's just say, it would have to be the square root of 2 over there, okay, because the radius, of course, for that is 2. Now, okay, just so you guys know that this 2, when I said the radius is 2, I meant this up here, okay? I did not mean that you need to use the formula for length of line, which gives you r, and that is how you get this radius of square root of 2 over here. They are not related, okay? This radius and this radius here, these values are given, and they do not come from within what's in that modulus sign. Just letting you guys know that. So this is an actual question. This is what the question looks like, and they will tell you to draw that diagram. And when you look at it, you have to learn that the modulus signs represents that, hey, there's a party happening with this complex number 1 plus I. So the first thing I'm going to draw is that complex point, 1, 1, which we have already drawn here. Okay, and then what kind of party is happening? I see modulus signs. So whenever there's modulus signs on one side of your equal sign, which is here on the left hand side, it means that you are being asked to draw a circle. Okay, so we are going to draw a circle here. We'll try our best to draw the circle. Oh, I'm drawing this freehand, people, okay? Looks like an ellipse, but okay, yeah. Now, there's a reason why I'm trying to make it intersect at certain points, okay? So because we're drawing a circle and we're trying to draw a circle around the points 1, 1, we have to acknowledge the fact that this is a graph, okay? And because it is a graph, above this point, a circle has a radius. So that means from here to here, if this value is 1, this should be 1 plus root 2 on average. Similarly, from here to here should also be, if this value is 1, it should be 1 subtract root 2 going down. This value up here should be 1 plus root 2. And similarly, from here to here, this should be 1 subtract root 2. So when you're drawing your circle, you kind of want to make sure it hits up certain values on your sketch for accuracy purposes. So to make it easier, if I were to just scroll down a bit over here, right? Let's just say that you had to draw a circle and your center was the values 2, -1. All right. If you had to draw a circle and say the radius of the circle around that was 1, then that would mean if this value is 2 here and this value is -1, okay, let's think about it for a moment. Then this value is 0, this value is 1. If this is the center of the circle, going up, a radius of 1 would stop here. That would be the top of the circle, wouldn't it? From this point here, if the radius of something is 1, then we would have to go down 1. That means the circle would end here. Similarly to the left, our circle going from 2 would end here. And then similarly, our circle starting from 2 would end at 3. So if you really had to draw an accurate circle, you have to make sure that your circle cuts all of those 4 points for accuracy purposes. Okay, some students use their compass and they just simply, because it's a graph paper, they just simply open out their compass to the respective radius and they just draw a circle, because a sketch can be a little bit more work sometimes, and you feel free to do that if that makes you do it faster. Okay, whatever works for you. But when you're doing your sketch of your circle, people, please make sure it does not look like mine. Okay. All right. So that's the first type of locus of a complex number, when there's a party taking place within a certain circumference of where it's all at. Okay. So the center of the party is over here and it has like a circle around it. All right, so, and it's represented by this kind of modulus sign there. All right, and please take note that sometimes you'll see questions look like this. They will have a z minus 2 plus I, say being equal to 1, and then students will tend to plot negative 2 with positive 1, and that is actually incorrect. If you notice, all right, if you notice, the format is z subtract c, where c is the actual complex number or complex point you want to plot. So you have to put it in that form first. So to put it in that form, you actually have to change signs. If you want this to be a minus with something, then that means these signs are actually going to change inside. So you'll really be plotting the coordinates x and y 2 with negative 1. All right, still the same radius of 1. All right, guys, so just take note of those little itty-bitty details that matter a lot when it comes to plotting diagrams on a complex plane. They're very basic, but because there's so much to know, you'd have to keep practicing a lot to get the hang of the different types of diagrams you have to draw. So coming up next, I'm going to show you guys another type of locus. It's not a circle, it's a straight line. All right, so that's up next. Okay, so next up, what kind of other conditions do we have? Well, the other one is called a perpendicular bisector of a line. All right, so let's get set up here, and straight away let me show you guys the format for what the condition looks like. So when I say condition, I mean that this is what you will see the question coming like. Okay, so condition, let's just say they ask you to plot the locus of C to satisfy the following conditions: the modulus of C minus A being equal to the modulus of C minus B. So this format is really easy to recognize because you will always have the presence of the modulus signs on both sides of your equal sign. In the previous example, if we just go back for a second, for the circle, you had that modulus taking place on one side, and on the right hand side you just had a number, which is a radius of a circle. Okay, but for something to be a perpendicular bisector, you will have the condition where you're seeing modulus signs on the left and modulus signs on your right. And this is actually way easier to draw than the circle. Here's why. Let's set up shop. Let me show you guys. So if we had to draw that, first of all, I would draw my complex plane. Okay, real part of C and the imaginary part of C. And let me give you guys an example of a question. So what if we had to draw the modulus of C minus 1 minus I, curved brackets here, is equal to C subtract 1 plus I. Okay, how is that going to look? Is it going to be two circles intersecting? No, because we have two modulus signs on either side. We have not been given a radius, so we cannot draw a circle at all. But what we can do is we can always see that complex number in both cases. In most conditions, in all conditions, you're going to be given the complex number to plot that point. So for this first case scenario, it's in the form z minus a. The brackets are already there. So from this, we can see we have the x value of, or rather, let me just pull out the coordinate. 1 minus 1, and the coordinate we'll be plotting here is simply 1, 1. All right, so on the left hand side, that complex number a is going to be 1. Okay, so this is 1 with negative 1. All right, so that's all the way down here. So let's call that 1, negative 1. All right, and the next one is 1 with positive 1. That's all the way up here. We'll call it 1 with positive 1. Now all we have done is simply we have sourced the two locations of the actual complex numbers a and b, and we plotted them on the complex plane. Now what we're going to do is simply just draw a little connector line to them. You know, this is a straight line connecting both of them. Why are we connecting them? Because based on the condition we have been given, they are connected. They're connected with an equal sign, okay? And what this condition allows to take place is that whenever you have two complex numbers connected in such a manner where the modulus of each other is equivalent, then the actual location of this is the perpendicular bisector of this connector line. So then what you need to think about is what's the exact halfway point between this and this. You have to actually think. It cannot just be a sketch. If this value is +1 and this value is -1, then the center of that is actually at 0, passing through the origin or the real axis. So the answer or the diagram that represents the condition of two moduluses being equal to each other, where we have the complex numbers in each modulus, is represented by this horizontal line in red. This is the perpendicular bisector, okay, of a line, right? So whenever you see something looking like this and they ask you to plot this diagram, it's just going to be a straight line. It's going to be a perpendicular bisector of the line which connects this point to this point. A lot of students forget it's not the connector line, and they connect both points and they say that's the answer. It's the perpendicular bisector. So please do not forget to take note of that. Okay, so that's the second type of diagram that happens. Let me take you guys to another one. Hold up, coming on next. Okay, and we're back, and I'm going to name this one. So before we did a full perpendicular bisector, this condition allows for a diagram to look like a half of a line. All right, half of a line. And it's really easy to recognize. Here's how the condition looks, guys. Here's what the question looks like. Whenever they ask you to draw something on the complex plane system, and it's going to come out looking like half a line, it always has this format. They'll ask you to draw the arg, but here's the difference, right? You're usually accustomed to seeing just the argument of z, right? Well, this one is the argument of z subtract a complex number there, all right? And it's equal to an angle. So do not confuse this with the formula argument of theta. All right, guys, do not confuse the two. This is actually a half a line. Let me show you what it looks like if you were ever asked to plot it. I'll show you an example. So we have our nice, beautiful real axis here, and we have the imaginary axis here. And let's just say, for example, they asked us to draw the argument. Let me write it up here. The argument of c subtract 1 minus I is equal to pi on 4. Okay, now remember, you need to make sure this looks just like this. So you kind of have to insert brackets. Once again, this is where a lot of students tend to forget to put that within brackets, which means that signs will change. Okay. All right, now it's in the form of c minus a. So what you're really plotting, if you look at it, is the point 1 with 1. So if we plot the point 1 with 1, that lies right here. All right. And now we're gonna, hold on, let me draw this a little bit not in the way of where I want to write stuff. So usually you're accustomed, when you have to draw an ARGAND diagram, you connect from the origin, go that direction. But this is a special type of line, okay? Wherever the point lies, remember, the aim of all of these diagrams is about the locus, where our central location is actually that complex number that we first plot, and everything happens kind of around it. It hovers around. So therefore, because this is the start, we're actually going to draw a dotted line to kind of represent where our locus is happening or taking place, and we're not going to connect it to the origin. Instead, we're just going to draw or continue our vector going all the way up from this point 1, 1. So the locus of this is actually just half a line. It starts at the point 1, 1, but it does not include it. So when you're drawing it, you actually have to try to draw it with like a open space, showing that the point 1, 1 is not included. And there's a special way, a special wording that you have to use when you're describing this diagram, because a lot of times they'll ask you, sometimes they can bring this for multiple choice, and they'll ask you to describe the locus of this complex number. And if they ask you to describe the locus, all right, if they ask you to describe the locus or the location, you're gonna say that it looks like it's half a line. Okay, it's half a line, and it starts at the point 1, 1, but it excludes the point 1, 1. Okay, so make sure you mention that. And because they gave us this aspect of it, we're gonna pop in that pi on 4 onto our diagram, and we're gonna say that it forms an angle of pi on 4. Okay, pi on 4 radians with the real axis, or however you want to write it, with the horizontal axis, with the real axis. All right, so that's how you would describe it. And please revise this wording, this description. It comes up a lot in past paper questions, right? They will ask you to describe the locus of this complex number, right? So that's what it always looks like. It looks like a dotted line on one end, and it's like missing the starting point from being a part of the answer. And yeah, that's pretty much what it looks like. Okay, if it happens to fall in a different plane, you will see it will just be on a different, let me just give you an example. For example, if we have it in the third quadrant, sometimes it can come across as, if this is your point here, okay, you still have to make sure you make that horizontal line, and then you will still have to make sure that your line is going up. Oh, sorry, wrong way. Make sure that your line is going up in a particular direction based on the angle you're given. Usually in this third quadrant, you could be given big angles like 3 pi on 2, etc. So it could go this way. Now you can also have it going this way as well, with smaller angles like pi on 6 and stuff like that. But once you see answers with this dotted line, or diagrams with these dotted lines, they're all considered half lines, okay? Where they start at a particular point and they make an angle of something to the real axis. All right, guys, so far that we have learned to draw circles. We've learned to draw perpendicular bisectors, where you have modulus is equal to modulus. And now you guys have learned to draw a half a line. Finally, up next, we're going to learn about one more type of straight line system. Okay, so hold on, I know it's a lot to absorb, but you'll get the hang of it. It's not hard. Okay, and the last and final one, a straight line, another straight line. But the format looks as follows. Okay, so it looks like z is equal to a plus lambda b. Now, please do not mistake this with a plus ib. Lambda is not the same as the imaginary identifier. Okay, guys? So let me expand by example a little more of what this form may look like on an exam. They can ask you to plot or sketch the locus of z in a question like this. I'm taking this from y'all's favorite textbook so that you guys can look back on it. All right, so let's just look at this carefully. Now, obviously, this and this are all complex numbers, so that must mean that A and B belong to the complex number system, okay? And lambda is just another real number, okay? So letting you guys know that. So whenever you have to plot the locus of a complex number and you're seeing a case scenario where it's like a complex number plus another complex number, and one of the complex numbers has like a constant attached to it, like lambda, alpha, beta, gamma, it doesn't matter, but it's like a real number. What this is going to look like on, if you had to graph it onto a complex plane, is that it's going to come across as a straight line. So let me show you guys this one. All right. So first of all, we're going to have to look at the first part, A. All right. So looking at this part down here, this gives us the coordinates -1 with 2. All right. So what we're going to do is we're going to plot that -1 with 2. -1 with 2, let's just say this is 1 and this is 2. I did not label my axes, but we'll get to that. Okay, so this is the point, -1 with 2, this is 3 up here, etc. Okay, and I'm feeling weird I didn't label. Let me put in my labels. Okay, and this is my real part of C. Everything's happening up top and I have so little space. All right. Now, because it's a sketch, what we can do is we can pretty much just go ahead and we can just like draw a line kind of passing through that point. All right, such that it's just a straight line. And then the second part that has this 3 with this 4, we're going to also plot that point on here. So let's just say this is 1, this is 2, this is 3. Let me see if I could fit 4 up here. Then I'll have to kind of move this. 3 with 4. And 3 with 4 falls somewhere over here. Okay. So the first part, A, what we're going to do is we're going to say that the locus of Z is a line which actually passes through A. Okay, so in order to get this line in the correct orientation, because I mean, it's just a point. How do we even determine which direction that straight line has to be angled to? Well, the thing is, the locus has to be parallel to wherever the point B is. So it's kind of like you have a graph and you have 2 random points happening, like they're just like there. Now these 2 points are relative to each other such that they have to if you were to draw 2 lines on each one individually, those lines should be parallel to each other. And I mean, there's probably a ton of ways you can do it. You can draw it like this, you can draw it like this, you know. But the main thing is that however you choose to draw or sketch your locus, you have to kind of make sure that it's parallel to a line that would pass through the points 3, 4, right? So to make a better average, what they did is the part associated with lambda, right, which is the point 3, 4, they want you to make sure that that part is always connected to your origin. So in a sense, what you do first of all is kind of like draw a dotted line connecting the origin to that secondary part with lambda, and that is what gives you the direction as how your parallel line is going to flow. So now that you have this aspect here giving you some kind of focus, then you can go ahead and draw your true answer. Now, you're probably wondering, we have 2 parallel lines, one being dotted, and we have a straight solid line. Which one is the answer? Your answer, or rather, if I were to write it on screen as a description, your answer is that the locus of this question here, the locus of z being equal to a plus lambda b, is a straight line. It's a straight line passing through, okay, it passes through A, so it must pass through that your first point, okay, and it has to be parallel to B, okay, where B has to start from the origin. All right, so those are the key foundations to remember, and this is actually your final answer. This line here, this line in green is your final answer. The line that is actually parallel to B. All right, guys. Let me just show you another quick example on this one to clear it up. Okay, because I think this is the toughest one for some students to understand. So let's just say they wanted us to plot the locus of z being equal to 3 plus 2i plus lambda by minus 1 minus 3i. Always make sure that your complex numbers are in the form in brackets already, okay? So we know our answer has to pass through the point 3, 2. Okay, so say 3, 2 is somewhere here. Our answer must pass through this point. But how do we know which direction our line takes? We have to look at this point where it lies in relation to the origin. So -1, -3 is somewhere down here, okay? And if we were to connect this using a dotted line to the origin, we would get -1 with -3 somewhere down here, right? And this little dotted line tells us that, hey, our true answer is supposed to be parallel to that line. So therefore, this is our answer. This is the locus of what we're looking for. This is the location of where the party is happening, you know. The true party is centered around this point here, but you know, parallel, there's a sideline thing taking place, but the truth is the party is still, it's parallel to that, what's happening on the side, but the true party is still happening over here. Okay, guys? So I hope that's an easy way for you guys to remember it. There's so many different forms. There's 4 different types, like I said: straight line, half line, perpendicular, bisector, and finally the circle one. Certainly the circle one looks like the easiest, right? So 4 different conditions you can possibly get. I mostly see these questions in multiple choice if you're looking for them. And then if they have to come in like final exams, they can come in the form of more like inequalities and stuff that you would have to calculate. So like when we're getting a bit more into gear on doing like past paper questions and stuff like that, we'll probably do some questions on the inequalities, where you have like many of these forms being interloped over each other, kind of like an intersection of a circle with an ARGAND diagram, arg of z. Okay, so you might have like a intersection and they might ask for a particular region and stuff like that. So we'll get into those kind of more complex questions when we're doing some reviews. So I'm glad that you guys stayed all the way to the end. If I made any errors by accident, please leave a comment down below and I will make the necessary changes in my description box. It was good having you guys, and I'll see you soon for the last part 3 of complex numbers, where we'll be talking about the different forms that complex numbers can show up. Besides the regular z is equal to x plus iy, we have the exponential form and the polar form, and we'll also be doing a bit of De Moivre theorem, and that would be the close on last part of the complex numbers, and then we're done. So see you guys soon. Bye.